280.
I agree. And from either side?
Does not exist.
Perfect. That's all I wanted to hear. Okay. I would like to look at an example like this. In a moment, we'll choose. And something like this. Okay, from here. So let's look at sketch the graph of an example of a function f that satisfies all of the given conditions. So I'm going to copy, let's say, 17. There is more than one correct answer. Why I like these exercises is that they're making us think of what we just discussed. Okay, so I'm copying 17. And there is more than one correct answer. So the limit as x approaches -1 from the left of f of x, they say it's 0. Limit of f of x as x approaches -1 from the right, they say it's 1. Limit of f of x as x approaches 2 from either side is 3. What else is there? F of -1 is 2, and f of 2 is 1. Always check what I copy. I have no excuse, but I have these devices in front of me. So -1 from the left, -1 from the right. I think I copied that correctly. 2, 3. Yes, yes. Okay. So they want us to graph a function that fulfills the given conditions. Again, please try to understand. If you don't like to use it, create your own table. I'm fine with that. I love creativity, but please understand what I'm trying to do here. Okay, so the limit of x of the function when x approaches -1 from the left. Okay, so I have to have in the table -1 and -1 from the left. I'm using that parenthesis that we used at the very beginning of the class with graphing the piecewise defined function. So the limit is 0. So the limit of f of x as x approaches -1 from the left of -1 is 0. Done. From the right of -1 is 1. 1. See, they're not touching. Okay? Good. Done. The limit of f of x as x approaches 2 from either side. 2 from either side. Yeah, they may be touching. Potentially here, they may, but I'm not sure. We can create something like that. You can put a number in here if you want to. So it doesn't matter what else you add to it, as long as these conditions are fulfilled. You can add a 5 in here or a 10, whatever you want. But, and more, and horizontal asymptotes, and max, min, whatever you want. But these conditions have to be in. So the limit from either side is 3. So I'm going to put here 3. I'm going to put here 3. I may choose to put a full point or not, but this is taken care of. Now, I finally got to f of -1, which is 2. Aha! So that's what they want. They are giving us the 2. So we can make that one up. We can make up other things, anything that we want, but not that one. Good. So that is in the table. And f of 2 is 1. Ah, okay. So that's what they want. So it's all clear. I will start by graphing first the points that I have. And what do I have? I have -1.
So real quick,
yes?
Hypothetically, the only situation like this where you'd use brackets instead of a parentheses based on what they're giving us now would be if it was like...
Or if you want to make your own. So I have the bracket when I have the equal symbol.
Yeah.
So I have the parenthesis when I don't. So you can...
Would there be no way of knowing that in this?
If it's not given to us, you can create your own. Okay. They don't care what else we add in here. They only care that these conditions are in. So for example, if you want, you can add at 0 a vertical asymptote. So you can put infinity here and infinity here. You can add anything you want. As long as
Okay.
the given conditions are in, the creativity has, the sky is the limit. So I start with -1, 2, which is a full point. But then -1, 0 cannot be a full point. And -1, 1 cannot be a full point. Otherwise, this would not be a function. And I'm going to do this, whatever you want. But I make sure that it is a function. You cannot do this because it will not be a function. And 2, 1, full point. And 3, and 2, 3, 2, 3. So 1, 2, 3, open point. So here's my graph. Here the limit, as you see, that's why this table is so useful. Here the limit exists. Who cares that the function is not filled in here? No, the limit from the left and the limit from the right are 3 and 3. So then the limit from either side of 2 exists, is 3. The function value is 1 at 2. Okay, but here the limit does not exist because the limit from the left is 0 and the limit from the right is 1. So this is D and E. Who cares that the point is here? The limit does not exist because the tendency on this is 0 and the tendency on this is 1. But here the limit exists because the tendency is 3 and the tendency is 3. And this is my graph. You can do whatever. You can go to a vertical asymptote. You can come back from a vertical asymptote. You can come back from here. It doesn't matter. So you can add whatever you want. So I did not add this in the graph. I was just giving an example. I know, looking at only my phone tells me the time. So I know I have 4 minutes left. So just allow me to show just one example with the infinite limits from the book. And I'll stop, I promise. If I ever go over, please, this is not disrespectful. I'm disrespectful to you if I don't watch the time, okay? So always tell me if I'm close or if you think that I'm going to talk more. Okay, so what about 39? So 39 is limit as x approaches 0 from either side from natural log of x squared minus x to -2. Okay. So I think that this limit should not be at this point presented in the text, but it is. So anyone remembers how to change this into something else? What does it equal to? X to -2.
Would it be 1 over x squared?
Brilliant, of course. Thank you very much. So this is limit as x approaches 0 from natural log of x squared minus 1 over x squared. Why I think that this limit should not be in this section, you'll see later. I'll remind you of this. So now, what happens with 1 over x squared? Okay, so let's talk about this for a moment because we already talked about this. We know the graph of this natural log. If it's of x or x squared, it doesn't matter. It still looks like this. There is no discussion there. And if it's x squared, it also has both branches, right? That's the only difference between, so this is natural log of x squared and natural log x is just one piece. But if it's x squared, we have both branches. Now, the graph of this, I should have not picked this problem just to finish it up. I'm going to do it again on Tuesday because I would like to finish it. So the graph of 1 over x squared is this. Okay. So notice that as x approaches 0 from either side for this graph, this will be negative infinity. As you see, goes to negative infinity. What happens here is, so this is the graph of 1 over x squared. So as x approaches 0 from either side, I have positive infinity. So this is negative infinity, but this is minus infinity. So without a graph, it's more difficult to explain what this is happening here. What is the answer? So this approaches negative infinity. This approaches infinity, but with minus in front. So negative infinity minus infinity, what will the answer be?
0.
So negative infinity minus infinity.
Oh, minus, not plus.
If it's plus, it's a tragedy, I should say. No, infinity minus infinity is one of the 7 indeterminate cases. This is a big problem here. But no, in this case is negative infinity minus infinity, which is not an indeterminate case, and the answer is negative infinity. I'll stop, I promise. So